A Ufer grounding electrode system, while beneficial, might not always guarantee a circuit breaker will trip under ground fault conditions, especially with an open service drop neutral. Several factors contribute to this. Firstly, high ground fault current. The circuit breaker needs a certain level of current to activate its trip mechanism. If the grounding system's resistance is too high, such as 5 ohms, the resulting fault current may be insufficient to reach that threshold. Secondly, line-to-line faults. An open service drop neutral often leads to a line-to-line fault, rather than a line-to-ground fault. These line-to-line faults typically exhibit lower fault currents due to the higher impedance of the fault path compared to a direct line-to-ground scenario. System impedance also plays a crucial role. The overall impedance of the grounding system, which includes the Ufer ground, connecting wires, and any other grounding electrodes, affects the magnitude of the fault current. High system impedance restricts current flow, reducing the likelihood of the circuit breaker tripping. Breaker sensitivity is another consideration. Circuit breakers are designed with varying levels of sensitivity. Some breakers may not be sensitive enough to trip at the fault current level produced by a Ufer grounding system with a relatively high resistance. Furthermore, the physical characteristics of the ground rod itself influence its resistance. The length and diameter of the Ufer ground rod significantly affect its resistance. Shorter or smaller diameter ground rods generally have higher resistance, which can contribute to the overall system's resistance. To ensure adequate protection, several measures can be implemented. Firstly, additional grounding electrodes. Installing multiple Ufer ground rods or supplementing them with other types of grounding electrodes, such as copper-clad steel ground rods or concrete-encased electrodes, can effectively lower the total resistance of the grounding system and improve the flow of fault current. Secondly, high-sensitivity circuit breakers. Using circuit breakers with higher sensitivity increases the probability of tripping at lower fault currents. This is particularly beneficial when the grounding system resistance is higher. Thirdly, ground fault protection devices. Ground fault protection devices, which include ground fault circuit interrupters and arc fault circuit interrupters, provide an extra layer of protection. They work by continuously monitoring the current balance in a circuit and rapidly opening the circuit if a ground fault is detected, even if the fault current is relatively low. In summary, while a Ufer ground is a valuable component of an electrical grounding system, it's essential to understand its limitations. Relying solely on a Ufer ground with a resistance around 5 ohms may not be sufficient to guarantee circuit breaker tripping under all ground fault conditions, especially when an open service drop neutral is present. A comprehensive approach that combines multiple grounding electrodes, sensitive circuit breakers, and ground fault protection devices is necessary to ensure proper electrical safety and protection against ground faults. Section 250.53 A3 of the National Electrical Code, or NEC, addresses the requirements for supplemental electrodes. When a single rod, pipe, or plate electrode does not achieve a resistance to ground of 25 ohms or less, it must be supplemented by an additional electrode. This supplemental electrode could be another rod, pipe, or plate electrode, or it could be a ground ring or other approved type of grounding electrode. The two electrodes must be separated by at least 6 feet. This requirement emphasizes the importance of achieving a low-resistance grounding system to ensure effective fault current dissipation. Section 250.56 of the NEC covers the requirements for bonding jumper connections. Bonding jumpers are used to connect different metal parts of the electrical system together, such as metal conduits, enclosures, and equipment grounding conductors. These connections are essential for creating a low impedance path for fault current to flow back to the source, which helps to ensure that the circuit breaker will trip quickly in the event of a ground fault. Section 250.66 of the NEC specifies the size of the grounding electrode conductor. The grounding electrode conductor connects the grounding electrode to the neutral bus in the service equipment. The size of the grounding electrode conductor is based on the size of the service entrance conductors. Ensuring that the grounding electrode conductor is properly sized is crucial for providing a low impedance path for fault current to flow back to the source. Article 250 of the NEC is dedicated to grounding and bonding. Grounding and bonding are essential for electrical safety, as they provide a path for fault current to flow back to the source, which helps to ensure that the circuit breaker will trip quickly in the event of a ground fault. Grounding also helps to protect people from electric shock by providing a low impedance path for current to flow back to the source if they come into contact with a live wire. Section 250.4 of the NEC covers the general requirements for grounding and bonding. This section specifies the types of systems that must be grounded, the methods for grounding them, and the requirements for bonding different metal parts of the electrical system together. Section 250.24 of the NEC covers the grounding of separately derived systems. A separately derived system is a system that is powered by a generator or a transformer. This section specifies the requirements for grounding the neutral conductor of the separately derived system. Section 250.30 of the NEC covers the grounding of service-supplied alternating current systems. This section specifies the requirements for grounding the neutral conductor of the service entrance. Section 250.50 of the NEC covers the grounding electrode system. The grounding electrode system is the system of electrodes that are used to connect the electrical system to the earth. This section specifies the types of electrodes that are permitted, the requirements for installing them, and the requirements for connecting them together. The NEC provides specific guidance on size and grounding electrode conductors based on the size of the ungrounded service conductors. For example, according to NEC Table 250.66, if the service entrance conductors are 2/0 American wire gauge copper, the minimum size of the grounding electrode conductor is 4 American wire gauge copper. If the service entrance conductors are 3/0 American wire gauge copper, the minimum size of the grounding electrode conductor is 2 American wire gauge copper. If the service entrance conductors are 4/0 American wire gauge copper or 250 kcmel copper, the minimum size of the grounding electrode conductor is 1/0 American wire gauge copper. It is always important to consult the latest edition of the NEC for the most up-to-date requirements and to consult with a qualified electrician or electrical engineer to ensure that the grounding system is properly designed and installed. In addition to the NEC requirements, there may be local codes or regulations that apply. It is important to check with the local authorities to determine what these requirements are. The installation of a Ufer ground, also known as a concrete encased electrode, must adhere to specific requirements outlined in NEC section 250.52. A3. This section mandates that the concrete encased electrode must be encased by at least 2 inches of concrete and be located within the bottom of a concrete foundation or footing that is in direct contact with the earth. The electrode must consist of at least 20 feet of either bare or zinc galvanized or other electrically conductive coated steel reinforcing bar or rod of not less than 1/2 inch in diameter, or consist of at least 20 feet of bare copper conductor not smaller than 4 American wire gauge. These specifications ensure that the electrode has sufficient surface area in contact with the earth to provide a low impedance path for fault current. When installing ground rods, NEC section 250.53. G provides guidelines for driving multiple ground rods. This section states that if multiple ground rods are used to meet the requirement for a low resistance grounding system, they must be spaced at least 6 feet apart. This spacing helps to ensure that the ground rods are effective in dissipating fault current into the earth. The NEC also addresses the use of aluminum and copper grounding electrode conductors. Section 250.64 states that grounding electrode conductors must be securely fastened to the surface on which they are carried. A grounding electrode conductor of aluminum or copper-clad aluminum must not be used where in direct contact with masonry or the earth, or where subject to corrosive conditions. Also, aluminum or copper-clad aluminum grounding electrode conductors must not be installed within 18 inches of the earth. There are also some common misconceptions about grounding and bonding. One misconception is that grounding is only for safety. While grounding is essential for safety, it also helps to ensure the proper operation of electrical equipment. Another misconception is that all grounds are created equal. The effectiveness of a ground depends on the resistance of the ground path. A low-resistance ground path is essential for safety. Another misconception is that a ground rod is all that is needed for grounding. While a ground rod is an important part of a grounding system, it is not the only component. A complete grounding system includes a grounding electrode conductor, bonding jumpers, and other components. It is important to understand the difference between grounding and bonding. Grounding is the connection of the electrical system to the earth. Bonding is the connection of different metal parts of the electrical system together. Both grounding and bonding are essential for electrical safety. When dealing with electrical systems, it's crucial to remember that electrical codes and standards, such as the NEC, are regularly updated. These updates reflect new technologies, improved safety practices, and lessons learned from past incidents. Therefore, always refer to the latest edition of the NEC and any applicable local codes when designing, installing, or maintaining electrical systems. Furthermore, electrical work should only be performed by qualified and licensed electricians. These professionals have the training, experience, and knowledge necessary to safely and correctly install and maintain electrical systems. They are also familiar with the applicable codes and standards and can ensure that the work is performed in compliance with these requirements. Attempting to perform electrical work without the proper qualifications can be dangerous and can result in serious injury or even death. In addition to the NEC and local codes, there are other resources available that can provide information on grounding and bonding. These resources include industry associations such as the Institute of Electrical and Electronics Engineers, or IEE, and the National Electrical Manufacturers Association, or NEMA. These organizations publish standards and guidelines on electrical safety and can provide valuable information on grounding and bonding. There are also many online resources available that can provide information on grounding and bonding. However, it is important to be sure that the information you are reading is accurate and reliable. Look for information from reputable sources such as government agencies, industry associations, and universities. When it comes to electrical safety, it is always better to be safe than sorry. If you have any questions or concerns about grounding or bonding, consult with a qualified electrician or electrical engineer. They can provide you with the information and guidance you need to ensure that your electrical system is safe and compliant. The principles of grounding and bonding extend beyond residential and commercial applications. They are also critical in industrial settings where the potential for electrical hazards is often greater. In industrial facilities, grounding and bonding are used to protect workers from electric shock, to prevent equipment damage, and to ensure the reliable operation of electrical systems. Industrial grounding systems often involve more complex designs and require more sophisticated equipment than residential or commercial systems. For example, industrial facilities may use multiple grounding electrodes, grounding grids, and other specialized grounding techniques. They may also use ground fault monitoring systems to detect and respond to ground faults quickly. In addition to the NEC, industrial grounding systems must also comply with other applicable standards, such as those published by the IEE and the International Electrotechnical Commission, or IEC. These standards provide detailed guidance on the design, installation, and maintenance of industrial grounding systems. The NEC also addresses the specific requirements for grounding and bonding in hazardous locations. Hazardous locations are areas where there is a risk of explosion or fire due to the presence of flammable gases, vapors, or dusts. In these locations, grounding and bonding are essential for preventing the accumulation of static electricity, which can ignite flammable substances. The NEC specifies the types of grounding and bonding methods that are permitted in hazardous locations. These methods include the use of intrinsically safe circuits, explosion-proof enclosures, and other specialized techniques. It is important to note that the requirements for grounding and bonding in hazardous locations are very strict and must be followed carefully to ensure safety. Grounding and bonding are also important in telecommunications systems. In telecommunications systems, grounding and bonding are used to protect equipment from damage due to lightning strikes, power surges, and other electrical disturbances. They also help to reduce noise and interference in telecommunications signals. The grounding and bonding requirements for telecommunications systems are specified in the NEC and in other applicable standards. These requirements cover the grounding of telecommunications equipment, the bonding of telecommunications cables, and the protection of telecommunications systems from lightning strikes. In addition to the technical aspects of grounding and bonding, it is also important to consider the human element. Electrical safety training is essential for all workers who work with or around electrical equipment. This training should cover the principles of grounding and bonding, the hazards of electricity, and the safe work practices that must be followed to prevent electrical accidents. Workers should also be trained on how to inspect electrical equipment for damage and how to report any hazards they find. A strong safety culture is essential for preventing electrical accidents. This culture should emphasize the importance of following safe work practices, using appropriate personal protective equipment, and reporting any hazards. Management should also provide adequate resources for electrical safety training and for the maintenance of electrical equipment. Regular inspections and testing of grounding and bonding systems are also essential for ensuring electrical safety. These inspections should be performed by qualified personnel and should cover all aspects of the grounding and bonding system, including the grounding electrodes, grounding electrode conductors, bonding jumpers, and other components. Any deficiencies that are found should be corrected promptly. Testing of grounding and bonding systems should be performed using calibrated test equipment. The test results should be documented and should be used to track the performance of the grounding and bonding system over time. By following these guidelines, it is possible to create a safe electrical environment and to prevent electrical accidents. Grounding and bonding are essential for electrical safety and should be taken seriously by everyone who works with or around electrical equipment. In summary, the resistance of a Ufer grounding electrode system alone, especially if it's around 5 ohms, may not be sufficient to reliably trip a circuit breaker under ground fault conditions, particularly when there's an open surface drop neutral. Factors such as high ground fault current requirements, the occurrence of line-to-line faults due to the open neutral, overall system impedance, and the sensitivity of the circuit breaker all play a role. To enhance protection, consider installing additional grounding electrodes to reduce resistance, utilizing high-sensitivity circuit breakers, and incorporating ground fault protection devices like GFPDs and Ufers. Adhering to the NEC guidelines and consulting with qualified electricians are essential for ensuring a safe and effective grounding system.